Hello, class. This is Roberts at Shasta High School, and it's time to take a look at this evening's homework. So we're starting with question 74 and going all the way to question 79. The first question says Sam collected data in problem 4-4 by measuring the pencils of her classmates. Okay. She recorded the length of the painted part of each pencil and its weight. Okay, I gotcha. So the length of the paint, like normally they're yellow, but it could be purple or some other color. Length of the paint versus the weight. Now, I'm thinking right now that there's going to be an association there. And in my mind, what I'm expecting to see is that the shorter the length of the paint is, the less it's going to weigh, right? So it says graph the data on your calculator and sketch the graph on your paper. So our best friend, of course, for a situation like this is Desmos. So I'm going to jump to Desmos, and I'm going to ask it to allow me to add a little table. So from Desmos, I'm just going to hit plus. I'm going to go to a table, and I've got the values here. I'm going to say length of the paint is my independent variable, or x value. So I'm going to go 13.7, 12.6, 10.7. Hey, please fast forward if you know this. 9.8, 9.3, 8.4. You don't have to watch me type these. 7.2, 6.3, 5.2, 4.5, 3.8. Got it. And then I've got to enter the corresponding y value. So next to that, all right, we're going to start with, oops, right up here, we're going to start with the weight was 4.7 grams, 4.3 grams, 4.1 grams, 3.8, 8 grams. We've got 3.6 grams, 3.4 grams, 3.0 grams. There was a 2.8 grams, 2.7 grams, 2.3, and another 2.3. There we go. Now, I did notice recently that, I don't know if this was here last year, but if you hit zoom fit, it's a pretty good fit anyways, right? It shows what this data looks like. There it is. There's that data set. And if you want, remember, you can you can shift click around to spread it out a bit, but there is our data, right? And that's great. We can see the data. We can see the scatter plot. I can just do a quick sketch of that. Pretty nice looking. What's the first question? It says, graph the data and sketch it on your graph paper. Did it. What is the equation of the LSRL? Okay, we can find that so easily, right? We know this power, right? This is superpower. So I'm going to type y1 because my y values were they were in this list, right? Y1, because my y's are in list 1 there, y1. And then I type tilde, and then mx1, and then plus b. And just like that, I have the most beautiful, look at that. Look at that line of best fit. Y equals 0.25x plus 1.3 if I wanted to round. 1.3, yeah. I'd do 1.30. So if I was going to round that to the nearest hundredths, I would say y is equal to 0.25 times x, and then plus 1.30. So I am rounding to the nearest hundredths, but you can see the next place over is a 9 also, so it has to go to the 1.3. So I include this 0 to let the user know that it is rounded to the nearest hundredths. It just, this became a 0. So, and you can see that this line is slightly different. It's kind of hard to see, but it's slightly different than the other one. It looks like it's slightly above it. And that's just because, you know, it's a decimal approximation, right? So I'm just rounding to 2 decimal places, which is appropriate, I think. So that is my line of best fit. So that was one of the questions. What did it say? It said, what is the equation of the LSRL? Sketch it on your plot. So I've got it there, and I can sketch on my graph. The equation looks like y is equal to 0.25x and then plus 1.30. That's me rounding to the nearest hundredths. Next, it says create a residual plot and sketch it on your paper. Oh, so cool. You know, if I had a printer that worked at home, that would be kind of be useful because I could print these up. So let's go do a residual plot. So let's review that. So I'm back at Desmos, and if I want to create the residual plots, I just say residuals E1 plot. Now, it quickly created a list of all the residuals. They're here in list E1. You can see some of them are positive. Those are points that are above the line. Then some are negative. Those are points that lie below the line of best fit. If I want to create a residual plot, what that would properly look like is I put 0 kind of in the middle of my graph. I'm going to turn off the data points, turn off the line of best fit, and then I will kind of just stretch this a little bit. So one thing to notice is with this residual plot, the biggest number up here is like, this is 1/2 away and 1/2 below. So these are all less than a half. Like these are very tiny residuals, right? And what's also cool is you can click on these points and you can see, oh, when X was 3.8, that point had a positive residual of 0.059. So you can see it. Oh, and also this one looks like this is the biggest residual in the whole data set. This biggest residual is 0.148. And remember, sometimes we like to report back. Oh, maybe this is going to ask me. Let's leave that and go back to the questions because maybe they're going to ask me that question later. Let's go back to here we go. So the next thing it says create a residual plot and sketch it on your graph. So again, what does the residual plot look like? It looks like this is so unfair because I'm just grabbing that and then I just come over. Oh, I can't just paste it there. Oh well. Oh, actually, I can paste it over here. So here you can see I've got the scatter plot with the line of best fit. I've got the equation of that line of best fit. And then below, I have my residual plot. Wonderful. So as I look at that residual plot, I do not see like a high, low, high pattern. I don't see a pattern inherent in this residual plot. So I'm going to say that a linear fit is probably good for this model. So it says, interpret your residual plot. Does it seem appropriate to use a linear model to make predictions about the weight of the pencil? I would say yes, linear model looks good. And the reason why I would reject a linear model is if I saw some kind of a pattern in my residual plot, right? Because when I see some kind of a curving in the residual plot that says, hey, so for example, in this residual plot, let's just play pretend. Let's say that I got rid of some points. Let's say that this point was gone, that point was gone, right? I'm whiting out some points. I'll say this point is gone. Let's say this point was gone. Now, if that's all that I had for my residual plot, to me, right, it looks like I see this kind of high, low, high pattern. And when I see a pattern like that, it indicates that probably a nonlinear model would be appropriate. But when I come back and I look at all the data points we had, right, all of them, it seems like there's because there's a lot of variation there. I don't think that I would reject a linear model here. And then finally, the teacher's pencil, when it was new, had 16.8 centimeters of paint and weighed 9 grams. What was the residual? Consider the precision of the original data and use an appropriate number of decimal places. Okay, this is fun. So if I was to do this, okay, so there's an actual value right here, right? The teacher's pencil was 16.8, so I'm going to write down 16.8, and that's the X value. That was the length of the paint, and it weighed 6 grams, and that would be the Y value. And this Y value is the actual Y value, right? It's the actual Y. Now, the question is, what's the predicted Y? So in order for me to figure out the predicted Y, I'm going to go back to Desmos, and way down here, oh, I did not mean to move this around. That's unfortunate. What I'm going to do in Desmos, where did Desmos go? Come on, Desmos. Oh, there it is. What I'm going to do is I'm going to just put in the X value. So I'm just going to say Y is equal to, actually, I'm not even going to put Y. I'm just going to say the following. I'm going to say 0.25, I'm just going to use this for a calculator, times the length of the teacher's pencil was 16.8 centimeters, and then plus 1.3. So what I have here, right, with the 5.5, this is what the model predicts. How did I get that number? Pretty easy, right? I just took in and I put, instead of x, right, I did 0.25 times the length of my pencil's paint when it was new. So times 16.8 plus 1.3. So 5.9 is what my model predicts. So let's go back to over here. So my actual value was 6. The predicted value was 5.5. So what is the residual? The residual is, let's see. The residual is the actual minus the predicted value. Actual was 6. The predicted was 5.5. That means that my residual is 0.5. Right? Residual is 0.5. Not centimeters, 0.5. These were grams, right? Those are, the up and down values are grams. 0.5 grams. Okay, now the next thing it says, what does a positive residual mean in this context? Oh my goodness. So I think that what we're doing is we're using the length of the paint to predict the weight of the pencil. So I think if I've got a positive residual, that means that the pencil is heavier than expected. I think that's what it is, right? Because right now the model was saying my pencil should have weighed 5.5, but it was 6. So if I have a positive residual, that means my pencil weighs more than it was predicted to weigh. So I'm going to say for F, it means pencil, P-E-N-C-I-L, weighs, W-E-I-G-H, more than predicted. All right, that's it. Wow, that was quite a question, huh? Let's go to next question. Simplify. Okay. Ooh. So does it say no calculators? It doesn't say that, but you know what? I'm going to challenge myself. So if I'm wrong, I'm challenging myself. So this right here is the number 3 times 5, and that is the number 4. So I need all of them. So 4, yuck. So 4, there's no common factors at all. So 4 times 15 is 60. Oh my gosh. So my common denominator is 60. So in order to make this look like 60th, I'm going to multiply this fraction by 4 over 4. Oh, that's clever, right? I got to pat myself on the back for that. That's clever. And then this one over here, in order for this to be the common denominator, I need to multiply this one by 15 over. I never even thought about this, but I'm literally using giant ones to change these fractions so that they'll have the right denominator. So if I do this now, this first one's going to become, oh, that pen is just a mess. That needs to be way thinner than that. Let me make it here. I'm going to make this 44 out of 60. Okay. And then it's going to be a minus 3 times 15 is 45 out of 60. Really? 44 minus 45, that's 1. So this should equal negative 1 over 60. Now, everyone in my class knows I'm not historically good with the arithmetic. So out of curiosity only, I'm going to turn on this calculator, right? Where are you? There you are. And I want to check my work. So I had 11 over 15, and from that I was subtracting 3/4, and I'm predicting it's going to be negative 1 over 60. What? That's crazy. So that was just me wanting to see if I could do it. Let's look at this next one. Okay, I hate mixed numbers. I hate mixed numbers. Yeah, I don't like mixed numbers. Yuck. I'm going to get rid of mixed numbers. Let's see. 9 times 5 is 45, plus 2 is 4. So this is negative 47 over 9. And then minus 2 times 3 is 6. That's minus 7/3. Okay, so what's beautiful about this is they almost have common denominators. I only need to multiply, let me make this, I only need to change the second one. I'm going to multiply this one by 3 over 3. See? This giant 1 multiplying by 1 is going to make it so that the denominators are the same. So this is going to become, in the numerator, negative 47 over 9. And then I'm going to have minus 3 times 7 is 21 over 3 times 3 is 9. Same denominator now, right? So I'm looking at 47 minus negative 47 minus 21. 47, 21, 7, 8, 68. So I get negative 68 over 9. Okay, the thing that I dislike the most is I don't like entering mixed numbers. So if I was to do that, oh yuck. This calculator 5, and then I'm going to go 2, and then I'm going to go ninths. Okay, then I'm going to go minus. Actually, that's not bad. 2, and then I'm going to go 1. I'm going to go third, and I get, yeah, I've dealt with the fractions. Oh, let's do D while we're here. So we're dividing by 1/4. I know. There's a lot of 1/4 in the number 3. In fact, every single one of those numbers in 3, each one of the whole numbers has 4 of them. Oh, yeah. This is literally, this is what this is. This is negative 12, right? The number is negative 12. If I have negative 3 and I divide by, let's see, negative 3, and I divide that by 1/4. Yeah, I get negative 12. By the way, look, guys, I hope you're listening and just thinking about this. I don't care about my answer, right? I'm just playing this game to see if I can, and then I'm like, am I right? I want to check what's going on. So that's just this game I'm playing. So let's look at this here. Negative 7/8 plus 2/3, and literally this is plus 1/4. Okay, I'm gonna just do that. Now, what do I got? What's my common denominator here? This is 2, 2, 2. That's a 3, and that's 2, 2. 3 times 8 would do it, which is the number 24, right? My common denominator is 2, 2, 2, 3. Okay, I'm looking at that. Now, looking at that is useful to me because it kind of tells me what giant ones I need to bring in to switch to that denominator. So 8 needs a factor of 3. So I'm going to multiply this by 3 over 3. That giant 1 is going to make it so that we'll have a denominator of 24. This needs an 8. So I'm going to multiply this one by 8 over 8. And literally that will now have the denominator of 24. Yeah, it'll be 24. And then this last one here, 2, 2, this needs a 6. So you can see if I use 2, 2, I've got 2, 2 left over. So this needs a 6 over 6. So what are we doing here? This problem is going to become negative 21 over 24 plus 2 times 8 is 16 over 24 plus 1 times 6 is 6 over 24. 16 and 6 is 20. What is that? 16 plus 6 is 22. That's positive 22. And a negative 21, it's going to give me 1. It's going to give me 1/24. 1/24. You know what? I'm not going to check that answer. If I'm wrong, tell me about it. Move on. 76. It says for each of the following area models, determine what? Where'd that just go? What? Oh no. I don't. Oh my gosh. Just a minute. I gotta pause this. All over the place. Okay, so let's look at this. So if I've got 3y and I'm multiplying that by something to get 3y squared, I know what I had to multiply by was a y. So 3y times y is 3y squared. And then if I'm multiplying negative 4 times 3y, that's going to give me a negative 12y. So literally what this problem is this: what do you get when you multiply 3y times y minus 4? What do you get? I'll tell you what you get. That's equal to 3y squared minus 12y. Simplest form of the distributive property, right? Don't need an area model for that. Next, 3y times y is going to be 3y squared. Okay. And then if I multiply y times something, I get 5y. Well, that means this thing had to be a 5, right? Y times 5y gives me that. Let's see, 3y times something is giving me negative 12y. This would have to be a negative 4, right? Negative 4 times 3y is negative 12y. And then last, negative 4 times 5 would be a negative 20. So what problem is this? The problem is y minus 4 times the quantity of 3y plus 5. When you multiply that, what do you get? You get 3y squared. Now these two are like terms. They can be combined. 5y and negative 12y is going to be minus 7y and then minus 20. So the product of y minus 4 and 3y plus 5 is 3y squared plus minus 7y minus 20. I don't like, I'm struggling with my number 4s these days. I'm like thinking about changing up how I write them. I don't know. Maybe. All right, let's move on to the next problem. It says determine the slope and y-intercept for each line. Okay, so this first one is not in slope-intercept form. So in order to get it in that form, I'm going to begin by taking away 2x from each side. So I'm going to write 7y equals, I'm taking away 2x, minus 2x plus 14. I can see that on both the left-hand side and the right-hand side, I subtracted 2x. Next, I'm dividing everything by 7. 7y divided by 7 is y. Negative 2x divided by 7 is negative 2/7 times x. And 14 divided by 7 is 2. Okay, so my slope for this is down 2 to the right 7. And my y-intercept is going to be the number 2, right? So those are my parameters for that. For C, let's do it. We're here. On C, I can see I have a binomial divided by this 2. So what I'm going to do is divide each of them by 2. I've talked about this a lot in class, right? 4 plus 2 divided by 2 is not the number 4. It's not 4, right? This is not a giant 1. It's not. Erase that, Roberts, because it's not, right? What is that? That's 6 plus 2, right? However, if I divide both of those terms by 2, right? It's kind of like the distributive property with the division. I could divide both of them by 2, right? 4 divided by 2 is 2. 4 divided by 2 is 2, and 2 divided by 2 is 1. And sure enough, look at that. That numerator is 6 in the denominator. Oh, I can do that, right? I can. So 10x divided by 2 is 5x, and negative 2 divided by 2 is minus 1. So I get that this is what y equals. So I know the slope parameter is 5, right? Up 5 over 1. And my y-intercept parameter is negative 1. I could graph that right now, and I'd see that in Desmos. Right? Okay, this next one. Ooh, okay. Trying to trick me up here by switching up the order. So my slope parameter is negative 1/3. You see it, it's negative, and it's something divided by 3, right? So this is the same as, right? I could write this like this, I could write negative 1/3 times x. That's the same as what we have there. So my slope is negative 1/3, and my y-intercept is positive, right? It's positive 6. Sweet. Last one. My slope is the number 3, up 3 over 1. And my y-intercept is the number 0. It's going right through the origin. I have nothing. No y-intercept. All right, next. A deli sells 4-inch sub sandwiches for $2.95. It has decided to sell a family sub that's 50 inches long. How much should it charge? What is the unit rate in dollars per foot? Ooh. So I'm just going to say it's a proportion, right? I'm going to work as a proportion. So I'm going to say for for you get 4 inches if you spend $2.95. And I'm going to say that's going to be proportional to 50 inches for X number of dollars. That's what I'm going to say. So how do I solve this proportion? Well, it is a proportion, right? I can multiply both sides. If I want to solve this proportion, I can multiply both sides by 2.95x. Multiply by 2.95x. So yeah, if you have equal things and you multiply it by equal things, you get equal things. Over on the right-hand side, you can see that there's going to be this x over this x, which forms a 1. And over here, there's going to be 2.95 divided by 2.95, which forms a 1. So those are gone, and this equation becomes, on the left-hand side, it becomes 4x is equal to, calculator time. Oh, I've got a calculator on the screen already. Will this work if I go 50? Nope. Let me go click 50 times 2.95. It says that is 147.5. And then if I divide that by 4, I get $36.875. $36.88 if I round to the nearest penny. Yeah, how much should it be charged for? Show all your work. So I'm going to say you should charge $36.88 or 87 cents if you want to be generous. Generous, it's a half a penny, I don't know. $36.88. And it says, what is the rate in dollars per foot? So right now that's dollars per 50 inches. That's dollars per 50 inch. Oh, I'm gonna do this. Oh, you know what I'm gonna do, right? I want inches to go away and I want it to be dollars per foot. So I know that there are 12 inches in 1 foot. Oh, look at it. It's a giant 1. So that was 50 inches. So the inches over inches is going to equal 1. And now I'm looking at what? I'm looking at dollars per foot, right? I'm looking at dollars per foot. But I got to do the math. So I'm looking at 36.88 times 12. And then I'm going to divide that by 50. Okay, you say so. Let's see. There is... I got the... Okay. I'll leave the 0.875. I'm going to multiply that times 12. Yeah, and then I'm going to divide that by 50. I get $8.85, right? $8.85 per 1 foot. That's great. I mean, it is dollars per feet because it was dollars per feet. And I took that number and I just did the arithmetic, right? 36.88 times 12 divided by 50. It's $8.85 a foot. Okay, now the last question, 79. Yes, the last question. There's 2 parts and I've separated it with work from. Oh, look at these. Oh, yeah. Okay. So first thing is I'm going to start with the smaller base. The smaller base is 2. And sometimes I just start looking at multiples of 2. So I know 2 to the first is 2. 2 to the second is 4. 2 to the third is 8. 2 to the fourth is 16. Now you can see I can stop already because I needed to get the number 8 and I got it, right? But sometimes it's good to go the other direction too, like 2, not with that pen. 2 to the 0 power is 1. Anything to the 0 power is 1. 2 to the negative first is 1/2. 2 to the negative second is 1/4. 2 to the negative third is 1/8. Maybe I'd have some fractions in these in the future. So I'm just playing around. Here's my plan. This number 8, right? I can replace, right? That is the same as 2 to the third. That's the number 8. I'm raising that to the x power, and on the other side I got that's 2 to the 6th. If I simplify the left-hand side, multiply the 3 times the other exponent of 8, 3 times x is going to give me 2 to the 3x is equal to 2 to the 6th power. And hey, they both have a base of 2, so that means that 3x has to be the same number as 6. That means x has to equal 2. So what this means, and this is easy to check, right? If I take the number 8 on my calculator and I raise that to the second power, I get 64, and 2 to the 6th power better be the same. Boom, it is, right? So x was 2. Change the base, set them equal, solve. Okay, and then let's take a look at, oh, are you kidding me? Did I anticipate this or what? Look at this. Because I've set this up, I got 1/2 already dialed in. 1/2, I can see it. And you know what? I'm going to do this. I'm going to use the 4 also. So for this next problem, I'm going to use the 4 and the 1/2. So look, the number 4 is the same thing as 2 squared, right? I'm just rewriting that base. That's 4. 2 squared is 4, and I'm raising that to the 2x, right? So you can see what I'm about, right? They're both being raised to the 2x power. Boy, that covered that one up. That doesn't look good. Being raised to the 2x power. And it's the same number, right? This is the number 4, and that's the number 4. Now, on the other side, right, watch this. 2 to the negative first power. 2 to the negative first power, where'd that come from, Roberts? Oh, look, 2 to the negative first power is 1/2. 2 to the negative second is 1/4. 2 to the negative third is 1/8. So that's the number 1/2. And I'm going to raise that to the x plus 5 power. That's beautiful. Maybe. It is. It is. So when you look at this, like this number right here, 2 to the negative 1 is the number 1/2. Now, raising the power to the power, right? On this left-hand side, this is going to become 2 raised to the 4x. All I did was I multiplied this 2 times 2x. So that's going to become 2 times 4x. And on the other side, it's going to become 2 to the negative x minus 5. Yeah, you see it. I had to multiply this power to this power, so both of those got hit with that factor of negative 1. Now that my bases are the same, right, what can I do? I can set this exponent equal to this exponent and solve. Let me add x to each side. 5x is negative 5. Divide by 5. X is negative 1. X is negative 1, I think. Let's check that against the original problem. You know what? I'm going to do this. Negative 1, store that into x. Boom. My calculator thinks that x is negative 1. So I'm going to look at 4 raised to the power of 2x. Boom. That says 1/16. And on the other side, I'm going to have open paren. I've got 1/2 close parens. I'm going to raise that to the x plus 5 power. Will it be 1/16? I don't know. Let's see. Yeah, it is. Yeah. So x is clearly the number 1, right? X is negative 1. That was the value. And you can double check that right on my calculator. I can just say, what was x? Oh, yeah, negative 1. Very good. Well, that's it. That is the completed homework assignment for the evening. Hope you have a good night, and I look forward to seeing you in class again soon.